Hello everybody, welcome back. So the goal for today is to do a video to overview the general process by which we approach these kinds of optimization problems, which we'll be working on today and tomorrow. So here is a very typical example of this kind of problem. Our objective is to build a garden in the shape of a rectangle. And this garden is going to be built out of two different materials, stone and wood. So I'll have two parallel stone walls and two parallel wood walls. Now, the stone walls are more expensive, costing $15 per foot, whereas the wood walls are a little bit cheaper, costing $8 per foot. Now, here is the restriction placed on us as we are building this rectangle. The first restriction is on the size of the rectangle. We want the size of the rectangle to be 30 square feet. Not only that, but when we build this rectangle, our goal is to build it so that the overall cost of building the garden is minimized. So, two requirements. The area must be 30 exactly, and the cost must be as small as possible. Alright, so to begin with, I typically will go in and assign some variables to the unknown quantities that this question is looking for. So let me call L the feet, the length of the wooden walls. And let me call W the feet, the length of the stone walls. Let me just get some nicknames for these quantities. Now I'm going to try to use the unknowns L and W as I construct equations that represent my two sort of requirements, my two objectives as I'm building this garden. My first requirement is that the area must be exactly 30. So rewriting this in terms of L and W, I will say that length times width must be exactly 30. So I'm going to label this as a constraint because this is something that's holding me back from being able to build whatever garden I want. I can't build just any old rectangular garden. I have to build one of exactly this size. Now, my second requirement is to have the lowest possible cost. Minimize cost. So let me try and come up with an equation using the letters L and W that represents the cost of building this garden. Now, if I have L feet dedicated for the length in the wooden wall direction, and it costs $8 per foot to build a wooden wall, then the left wall is going to cost $8 per foot times the L feet of the wall on the left side. Likewise, for the right side, it's going to cost $8 per foot times the L feet of the wooden wall on the right-hand side. Additionally, we have got, let's see, $15 per foot cost in the stone wall direction, on the bottom, W feet, and on the top as well, $15 times W for the top wall. So in total, the cost would be 16L plus 30W. And our goal is to minimize that. Now, the quantity that you're trying to minimize, the quantity that you're trying either to minimize or maximize, this is called the objective function because it is your objective, it is your goal to minimize this. Now, when we say minimize, it brings me back to when we were talking about relative minimums and global minimums. And we found relative minimums and global minimums using the first derivative. Take the first derivative of a function, set the derivative equal to 0 to find the critical numbers, and those critical numbers were often the location of relative maxes and relative mins. So let's try and do the same thing here. Let's try and find the derivative of this cost. Well, we run into a small issue here because cost at the moment is a function of two quantities. Cost is a function of both L and W. So should I take ddL or should I take ddW to find the derivative? Well, the answer is that we're not going to do either of these right now. What we're going to do is actually go back to this constraint function. And we are going to use it to get rid of all but one input variable. We're going to use it so that we can transform cost into a function of just one variable. And here's what that process looks like. We can take the constraint function, LW equals 30, and isolate one of those variables, W equals 30 over L. And we can substitute that into our objective function and find that cost is 16L plus 30, not times W anymore, but I can substitute 30 over L into W's place. So this now gives me cost as a function of the letter L only. Cost as a function of L is 16L plus 30 times 30, so let's just go with 900 over L. Now cost is a function of L alone. So if I write cost prime, take the first derivative, it must be the derivative with respect to the only input we have, L. So that's 16 minus 900 over L squared. And if we set this equal to 0, then we will be on track for finding the critical values where probably we're going to have some minima living. So here we go. If I rearrange this equation, 16 equals 900 over L squared, then L squared equals 900 over 16. It tells me that L, since it has to be a positive quantity, should be 30 over 4. 30 over 4. Now, meanwhile, finding the width, we can go back and use the fact that the width was equal to 30 divided by the length. So 30 divided by 30 over 4 would be 4 units, 4 feet in that direction.